And we're live. Okay. Hello, everyone. I hope everyone is here. So we'll just do a round of announcements, and I'll walk you through the interface again, and then we can sort of move on with the invited talk for the second half. Um, so just to let you know, in case you haven't been with this is the stage area. This is where you are going to be attending all your talks. Uh, the stage area tab is available on your left. We have two stages, but right now you're just using one. This is the LH101 stage for all talks happening here. Just stay online and you should be able to see them once they're live. The reception area is the first thing that you see when you join in anyway. The lounge area is the place where you can join in. There are multiple rooms there. You can join in, talk to other people, exchange ideas, give a short round of talks of your own if you want to. You know, it's a more of the informal parallel level track that could happen there if you want to have interactions and stuff. Networking is more of a one-on-one randomized, introductions. You talk to someone if you want to, just join the networking session. If someone is online, you should find them, talk to them, break the ice, and go from there, right? The Expo tab has the coffee booth there available for you. You can go there, visit it, leave any questions if you have them, and look at the information that is available there. We also have the chat.scipy channel, which is available on chat.scipy.in. You should have got the registration link in your invite email itself. Please join there. We have different channels created according to the stages. We are putting up announcements and news there as well. In case you have any questions, you can ask them in the event or the stage chat here, most probably the stage chat here in the stage. But if you want to leave any questions for the speakers to see later, you can leave them in the chat.scipy channel as well. And most probably the speakers will be hanging around so that they can answer your questions, right? That's probably it. We will be sharing slides and stuff on the chat.scipy channel. The lightning talk form is live and you can see it pinned to the event chat stream. Please have a look. If you want to give a short 5-minute talk, that's the place to be, because you'll have all the attendees looking at what you want to talk about. And we also wanted to remind you, please follow the code of conduct. Please avoid being unpleasant to anyone. Follow the code of conduct. In case you spot anyone violating it or feel that somebody you have been violated, please get in touch with someone with the organizer tag in Hopin Chat directly through private message or on the chat.scipy channel on private messages. Thank you. I'll hand over the stage to Professor Prabhu to introduce our next speaker. Professor Prabhu, you're on.
Thanks, Ankit. Thanks for setting it up. Welcome back, everyone. I hope you had a quick lunch break, and I hope that you don't miss this talk, because Dr. Ajith has been giving talks at SciPy for, I think he's become a constant feature of the conference, and we are really grateful to him for always acceding to our requests. I think his first talk may have been in 2010. So this may be the 10th year or 11th year of his continuous talks at SciPy India. Dr. Ajith, the first time I came across Dr. Ajith was, I think, in a workshop somewhere in Kerala many years ago. And he made his characteristic presentation with a device. I think you saw a sample of this with Jitin today. It turns out Jitin is Ajith's son. So that was the same effect that he had on me many years ago, more than 10 years ago, when he was demonstrating the XPICE experimental kit with Python, interfacing it, and it was just the talk was just a total joy to behold, and it was very inspiring. So Dr. Ajith basically works at the Inter-University Accelerator Center in New Delhi. And he's been there for many years, and he basically works with instrumenting these accelerators, and he has been using Python for this for many years, and he's built his own microcontroller based instrumentation that allows people to do school and college physics experiments in a very inexpensive package that's completely interfaced with Python and open source. And Ajith Kumar has always been so passionate about open source and spreading the adoption of the scientific approach and being able to think in a using the principles of science and scientific thought. So it's really a pleasure to have him here today with us. He will be talking about using Python for building instruments. And I think he's going to summarize his experience over the many years that he's been doing this. Thank you, Dr. Ajith, once again. We take you for granted, but please do know that you are a highly valued member of this community.
Okay, thank you. Thank you. And so should we start now?
Yes, you can start. You can start.
Oh, okay. Thank you. The slide is visible, right?
Yes, and maybe you can make it full screen or remove the sidebar if you want. I will tell you at around 25 minutes when you can take some time.
So I just probably remove the camera so that it gets more space.
Yes, it will give you full space.
Is it okay now or to do something?
Can you remove the sidebar close the sidebar on the outline on the left?
Okay. So I have to do a full screen here. It's all right now, right?
Perfect. Yeah, I can see it. Great.
Oh, okay, fine. So let's continue.
Thank you.
Okay, good afternoon, everybody. So this, as Prabhu told, it's coming, again and again. I mean, it's more not like an invited talk. I would say it's an insider talk. So basically, see, we have already had talks where you need to really, strain your brain to understand, but this is not that kind of talk. This is something more like telling the story, how somebody someone without much of a professional programming experience get into the field of computer programming and try to do something on his own field, and how ended up using Python, and how Python was found very interesting and very useful. So I'll just start about that. And about me, most of the time I'm working on particle accelerators and more on hardware than software. Hardware means not even computer hardware, the real hardware like copper, aluminum, and stainless steel. So in all those areas, somehow Python has put its signature. So I'll just tell about that. And about that project you have seen, how Python can be used for developing small instruments to do science experiments. That actually what I believe is Python is a very strong tool to enhance science education. Not only experiments, even teaching theory by using the computational methods because of its simplicity and so easy to learn. So this is somewhat the background, because this is again, we have the comparison of the languages. Like when we start using one language where we get somewhat attached to it. So Python was not my first language. It was in Fortran long back, somewhere in 85. And then switched to Pascal. The reason was a control system which I was working in on an old PDP-11 computer was written in Pascal. So mostly the work was that time it's writing particle accelerator control systems and data acquisition systems. And at some point the PC started appearing and switched over to 8088, the very old PC, somewhere in 1987. So at that point, from Pascal migrated to C language because Pascal compilers were not that common. And the legendary C compiler, the Turbo C compiler on MS-DOS, that was my first tool. And then somewhere in 94, switched to the free software, or what we call open source, because these two terms are used, okay, its difference is ideological, but in the end result, or what you gain out of it's more or less converging. So, and I give a lot of importance to these open source and free software systems because that is something which we should go for many reasons. And after this, I continued with C and something like, say, 15 years. The only language was C, and many things were tried in between, C++, Java, but for actual use, it was always C. Then we decided to do something like making some equipment. Like you see, for doing science and electronics or electrical experiments, we'll have a lot of test equipment, like oscilloscope, function generator, power supplies, many things. And all were expensive. And in a research lab, it was not an issue. But when you try to take this to the teaching labs, to colleges, schools, cost is a consideration. So we started a project somewhere in 2005 to build low-cost lab equipment. And for that, obviously, when someone starts doing something, we always use the technology that we are familiar with. And since I was familiar with C language, and those days the interfacing was the parallel port of the PC, the first unit was based on that. So we made something like using a very old conventional, it may be a Pentium machine. And here you can see a box, a big metal box. And you can have external connections like analog voltages and all. And what you see here is an oscilloscope trace. And all the software was written in C. And the communication to this was done by writing a device driver in Linux. Actually, there was no device driver those days. It was earlier, it was part of the code. I mean, you write it and integrated the kernel code itself. But later on, the loadable device drivers came. So this unit actually had a device driver. So you talk to the hardware, and even this graphical user interface, initially we wrote it in C, and it looked like this, a very simple scope screen in C. It took more than 1,000 lines, and these widgets were used actually the actual X window, the other widgets, which comes with X window library. And it was found that it is almost, impossible, like it's very tiring to write application this way in C without any advanced graphics libraries. And those days, free library was not available for Linux. Even Motif was there very early, but that was also proprietary in those days. Later on, it was open sourced. And the added trouble was we wanted to write small code, and we wanted to train teachers to write code to develop new experiments. And there, C almost, miserably failed. And at that point, I did not know what to do, but the advantage was this entire project was open hardware, and it was on our website. And we were looking for people to contribute. And then somebody suggested you can use Python. That was Pramod. So he took this code which we have written, and the device driver he called from some Python program with a small library. And the good thing was he published it in the next Gazette in somewhere in 2005. This paper, Experiment with Unix and Python. So this 5 lines of code was just doing an experiment measuring the acceleration due to gravity by using an electromagnet and a loudspeaker. So what it does is it takes a metal ball, MS ball, hold it by electromagnet. Under software control, it releases from a height, say h, and measure the time it reaches the ground. When it touches here, the loudspeaker will pick up a small signal and tell the computer, okay, it has touched the ground. So a simple experiment, and code also became very simple. So at this point, basically, I was forced to learn Python. So that's how we got into Python. And what I found was it's very easy to, it was becoming extremely easy because earlier everything was done in C. Even graphical user interfaces were done in C. But the more important part was training non-programmers. That means we were training physics teachers who were not programmers. So they come for a training program, it is only 6 days long. And what we found is we could teach enough Python, the necessary things within a couple of days so that they can write simple scripts like that I have shown you and perform simple experiments. So that is where Python, really stood out. And GUI programs, writing them became very easy. And another part was the data analysis that Jitin has showed you in the morning, like all those data analysis things. And the code is always 2-3 lines. It was beyond comparison with what we were doing. So all these things finally resulted the entire project developing a series of equipment, and Python became the default language for that. So I'll just give a brief introduction. And in 2006, we just migrated from parallel port. The main reason was the PC's parallel port was vanishing, and went for serial port and then for USB. And this is the unit we released in 2006. These are all open hardware, and this circuit schematic, everything was distributed freely. And in 2011, we made another one. That was the first time the name, the XPICE, was given. That it's an acronym. It stands for Experiments for Young Engineers and Scientists. And after releasing this unit, and immediately another small one was developed, which was a much lower cost, and but at the same time it was more powerful because shifting to another family of microcontrollers. And after 2012, actually I did not do much because all this project was actually a filler. When there is not much work happening here, this was going on. But after 2012, many other things, our accelerator related work came, and this just slowed down. But in 2017, then Jitin made something and released as open source, and we just took it and called it as XPICE 17. So here you can see that unit connections were made for some experiments, you can see here. And now you can see this graphical user interface has become much more complex, and this is all written in Python using Qt, the graphical toolkit. So this is, the journey of developing this equipment and adding more features. Like it was mentioned in the morning, it supports different languages. So this is the GUI in Tamil, and we have now something like 6 or 7 languages. And here actually all these things are done by different people. And this is also done by somebody, because I don't know Tamil, this is done by somebody from Tamil Nadu. Actually Hari from Uti, he has done it. And again, actually converting this data acquisition into a test equipment, like measuring frequency, phase, and all those things became very easy because of Python. You can see you have digitized the data here, and you just fit it with an equation like this. And if you have 2 graphs, you get say phi1 and phi2. You subtract it and you get the phase difference, because here it is telling, okay, these 2 graphs, the phase difference is 45 degrees. And the advantage is, even in 12th standard, we are teaching all this theory, like phase difference between 2 waveforms once they pass through RC circuits and all those things. So this enables the students, if they are interested, they can practically verify all those things instead of just looking at equations. So that was the objective of doing all these things. And this is not the only development. And that time there was 2 students in Delhi. They were doing similar things, and you can see it here in this site, box 0. They made something which, again, it was more tuned to teaching electronics than science. So this is another development, but I think they have not continued it after a while. And there, I would like to say the main reason is not very many are interested, because our teaching still concentrates on, it's mugging up theory and not doing much practicals. So that is one reason it has not really been picked up. And as I mentioned, it is not only for doing experiments. When you teach physics and mathematics, like when you show some equations, it makes much sense if you can give a graphical representation. So Python is a very good tool for that. So for example, when you talk about the sine wave multiplied by when we talk about a damped sine wave, it is just a product of a sine wave and exponential function. So these 5-6 lines gives you a plot using matplotlib. It becomes so easy. And once you see this, then you can start experimenting by changing different parameters. Suppose if you change this number, what will happen? Say damping factor, what will happen to the graph, all those things. So it gives a feeling of, these terms like damping factor, frequency, and what it really means. The picture tells much more than an equation. And here, this is another very simple example I selected because what I have found is even people who are doing MSc physics, this what we see is our in household supply, there is a 3-phase AC. That means between neutral and any phase, if you measure with the AC voltmeter, you get a 230 volt. And if you ask even a physics student, like what is the voltage between two phases? And many want answers. Suppose if you connect the AC voltmeter between the two phases. And electrical engineers, on the practical side, they know it is 400 volts. But when you want to explain this to a high school student, if you bring in all these equations and phase difference, it doesn't make much sense. It makes it more cumbersome. But if you just plot the two phases, say 3 graphs, and plot the difference between two phases, you can see that the difference is going up. And just by seeing at the picture, you can show the difference is, suppose say this minus this. Since one goes up, the other goes down, the difference is more than any of the individual waveforms. So this way, one can visualize things, and instead of using long equations, one can convey the physics in a slightly simpler manner. Okay, this is again some of the applications, like given that Prabhu's Mayavi is shown here, but the difference is it's all running on a Raspberry Pi, even with the 1 GB, the old one. So that means running Python, you don't need a very high processor or anything. For most of the applications, a moderate machine does the job. This is something I found very interesting recently. Like, we normally design electronic circuits by making the schematics, then making layouts like this. So this is the printed circuit board. And I have been using this EDA, Electronics Design Automation software called CAD. It is again open source and now supported by CERN, the biggest vertical accelerator lab. So here someone has written some Python program, library. So you can define circuits in Python. Like you define a component here, and these components are in the CAD library. And then you make connections. You can see this wire is defined just, okay, this plus is equal to, so they have over this operator overloading. The plus sign now means, in this case, connection between two points. So that means a very complex circuit, I can just define it as a Python program and generate the netlist and get this drawing. So these are, this is the example of how Python is used by different fields. Okay, so since I have been using Python very heavily and trying to pursue other people to use it, so something like some 10 or 12 years back, somebody wanted to include it in a BSc mathematics syllabus. So at that point, they wanted a kind of book. There are dozens of Python good books are available, but still we wanted to have something slightly specialized. So you can come to this website here in this XPI's website. If you have the Python tab, you will find there is a book here. And also you'll find some videos and other examples. Nothing great, but it's all tuned to a particular area. I mean, teaching science. So this is the book. And so this is downloadable. You can come to this website and you can download the book. And the funny thing is, it also has a chapter on tech, because their syllabus, they wanted it. So it's that is how it came there. So now to something else, like as I told, I'm working in the field of particle accelerators, and this is a copper structure, and you can see a small gaps here, and the charged particles get accelerated through this when we close this and apply radio frequency power. So these things are designed by solving actually electromagnetic, the Maxwell's equation for a particular structure, and calculating the electric field, then tracing particles through the electric field using Lorentz equations. And computer codes are available to do all those things. So you can see this is from a program called Microwave Studio, which is used for designing cavities. But this was all done, and before going for the production, maybe fabrication of this thing, actual thing, and we need to actually cross-check the. Here I did a small Python code to cross-check, like you have the accelerating voltage when you give a charged particle, how the energy increases. So this cross-checking actually really helped me at some point, because one structure which we made and the program used were having some quirks, because it was not a well-documented program written by a Russian guy. And finally we found things were not correct because input was not properly specified, but the mistake was very quickly caught by writing some simple Python programs. So Python became very handy at that point to me. And now coming to our internal application on particle accelerators. And this is a picture of one particle accelerator beamline. And controlling that means actually you have something like 2000 signals from various power supplies and other devices, voltages, currents, and all those things. And you control through a computer. So this system, what we had is something like this. You have a network system where like some hardware crates are there with some interfacing boxes like DME and all. And that is connected to the accelerator. And then you have client machines where the operators sit and control the machine. So it is all written in C. And initially we didn't find how we can fit Python into that. But it turned out that on the client side, Python was it turned out that Python is having a big advantage here, because there are many groups who were working on small sections of the machine, and they wanted to access a small subset of things, and they were not programmers. So just by, to sum it up, just by writing a small Python module to communicate over this network, because Python also has a TCP/IP communication library, socket libraries are there, and we could write a small library, import it, and just one line of code, we could access any parameter from the machine. Like just this one line of code, the charging power supply voltage control, say 2.2 kilowatt, it sets it. And this is a link to something on the CERN site, and that where I want to mention is at CERN also they have a large deployment of Python program for the accelerator control, but most of the things are at a sort of, again I told you, not direct communication to the hardware, but at a client level.
Just 5 more minutes.
Okay, it's over now. Okay. So this is, some of the areas in the area, where we use in science and engineering, the applications of Python, and this is where I have been focusing most of the time. So to conclude, what I found is, like compared to other languages which I use, the development time is much shorter in Python, and it results in very, it's obvious, anyone who has used Python knows that. We also found the GUI development, the tools are there, and it's very quick. And the biggest advantage is, of course, the NumPy, SciPy libraries for these computation needs. And probably the most important is, rather than learning, teaching somebody who is not a programmer, Python seems to be a good choice. That means their Python probably qualifies as the first language for anyone because it's so easy to learn. But again, I would say we still use C because when it comes to a real-time measurement and running on very low resource microcontrollers, C still has a strong point because very close to assembler. So this combination has given optimum results. I mean, we use Python where it's strong and use C where it suits better. So that's the kind of story which I thought I would tell. Thank you.
Thank you, Dr. Ajith, for your wonderful talk again. We have some questions. So there's one question by Manikant Roy. It says, this is just a naive question, sir. You wrote module in Python to get higher performance. That's a question. You're asking.
No,
no, did you write code in Python and did you end up with higher performance? This is what I understand of the question.
Okay. So no. See, we use Python not from the performance point of view. See, we know that an interpreter the language is not going to give more efficient code than C or something. But what we found is it became very easy. I mean, to writing Python code because of the existence of the libraries. And the same code, as I told in the name example of that oscilloscope, I had real tough time writing a very rudimentary oscilloscope which just displays one trace. The code ran into more than 1,000 lines. And if we start adding more features, it would have gone into thousands of lines. But later on, after switching to Python, within 200-300 lines, the same job could be done. So it was not the efficiency, but the ease of development what prompted me to go to Python.
And the I control square slide. You had a slide there, and that he is referring to that slide when he's asking.
Which one?
You're saying that you write the.
Which
I don't know.
This one, or he's talking about regarding the accelerator control, or
yeah, no, he got it. He says he understood.
Or this one.
Yeah, okay. He got the answer. So, yeah.
Okay.
Yeah, so that's all we have. There are many people who have really enjoyed your talk. So thank you once again for being with us.
Thank you.
So you will be around on the chat, I imagine, for a day, so we can ask.
Yeah, sure. Yeah, and one more thing, yes. Prabhu. So with the current address, this is the last talk, because February my term here is over. So maybe next time you should again come to Kerala. So you started there, right? I'll be there to organize.
Some questions on the chat which you can answer, I guess, offline. We will invite our next speakers.
Okay, sure. Yeah. Okay, thank you.
Stop broadcasting for now.
Yeah, I just leave here now. Okay.